Welcome everyone to the second instance of the Mapp 3D Roundtables. What we would like to achieve with these roundtables, the spirit of these roundtables, is that we simply would like to make ourselves available to answer any questions that you might have relating to Mapp 3D, our new system design and prediction tool. For that purpose, we have these roundtables where we encourage you to have a dialogue. It's all about Q&A. For those that are new to us, we typically tend to conduct these webinars, and we have several Meyer staff joining us for these 3D roundtables because collectively we feel comfortable that we can answer any questions that you might have. What we typically tend to do at the beginning is do a brief introduction of some tips and tricks, some topics that we would like to cover, and then we would like to dedicate some time to Q&A. And as always, we would like to remind you that the primary support platform for Mapp 3D is the dedicated Mapp 3D help website, which you can also access from within the application by going to your main menu bar and click on help. This has animated GIFs of routine procedure. It has video snippets or clips from previous roundtables and whatnot, showing you how to do routine procedures. So as always, this is your primary support platform for anything related Mapp 3D. Today's topics are going to be how do I insert objects and geometry. Objects could be microphone and loudspeakers and whatnot. We're going to talk about the primitives, which are your 2D shapes and 3D solids. And then how do I change what we come to call the centroid? How do I change my reference point within a given primitive? And then how do I change my geometry? How do I modify my geometry using Boolean operations such as union, subtract, and intersect? Then a new feature within Mapp 3D, which is SPL. Attenuation has always been there since the very beginning of Mapp. And we need to discuss about that because it comes with certain rules of engagement. And then finally, how do I tweak my SPL range and resolution settings for quick design and some optimization strategies for fast predictions? Starting with how do I insert objects, loudspeakers, microphones, and geometry into my model view? Well, before doing, there is something that you need to be aware of, which is that we're working in 3D space. We have X coordinates, Y coordinates, and Z coordinates. And last time we already talked about multiple viewports, which is really convenient, but it also determines that depending on your camera angle in a specific viewport, that objects, microphones, and loudspeakers will snap to the drawing plane normal to your viewing axis. So whenever we're working in a plan view or a top view, then we're observing the XY plane. And our viewing axis is the z-axis. We're watching along the z-axis on the xy plane, and that means that if I introduce geometry, loudspeaker, or microphone, that the z-coordinate will default to 0. The object will snap to the xy drawing plane. Whereas if I were to work in the viewport showing me my left view or my cross-sectional view, then I'm observing the xz plane along the y-axis. And if I were now to drop in a piece of geometry, then the y-axis value, the y-coordinate, would default to 0. And finally, if I'm working in a transsectional view, looking at the stage from front of house, then I'm observing the YZ plane along the x-axis. And then if I introduce a piece of geometry, then the x value will default to 0. And this is something to be mindful of, that depending on your viewing axis, normal to the drawing plane, one of those three coordinates will always default to 0. It will snap, so to speak. So here we see the project file that we've used before. I see an isometric view of a familiar looking spacecraft. And let's go to multiple viewports at once by clicking on multiple. In the top left corner, I got my isometric three-dimensional view, whereas in the top right corner, I got my top view. And in the top view, we're basically looking, and I can make you appreciate this, we're basically looking at the XY plane, okay, from above, indicated in yellow. So that's the drawing plane that you're looking at in top view. Whereas if you're working in the left view, which is your viewport in the bottom right corner, then you're looking at a section view. You're looking at the XZ plane, which I can make you appreciate by revealing this two-dimensional shape, which is the drawing plane in the bottom right corner. And finally, if you're working in the front view or back view for that matter, which you can choose with the drop-down menu. If you're working in the front view, then you're looking at the YZ drawing plane indicated in cyan in the bottom left corner. So there you have your three drawing planes, and together collectively they make up for a three-dimensional isometric view, as you can see in the top left corner. So let's hide that familiar-looking spacecraft and only keep those three two-dimensional drawing planes and start introducing today's first geometry, starting with the free draw tool. I have a layer already ready that has a white color assigned to that. Okay, notice that that layer is called free draw. I'm going to triple click on that layer. It's now blue. This is now my active layer, and that means that if I start drawing once more, then now my diamond better be white. Okay, so there you see the diamond shape that I'm about to draw, the diamond shape, and now I want to close that shape. Okay, I currently have three lines that are connected by three vertices. Now I want to close my shape. All I have to do is press the C key, as in C for close. If I hit C for close, notice that my diamond shape is now closed. Also notice that it's living in the XY plane. It's flat, living in the XY plane, because when I inserted the free draw within this viewport, then the Z coordinate defaulted to 0. So let's draw another shape, but this time let's do it from the left view. And this time I'm going to draw a triangle. So let's try this again. I'm going to draw a triangle. Okay, I'm going to hit C for close. Okay, three lines, three vertices. And notice that this shape, this redraw shape, is now stuck. It's snapped to the XZ plane because along this viewing axis, which is my Y-axis, the Y coordinate defaulted to 0. And finally, let's go to our front view. And in our front view, draw a square. So I'm going to make an attempt at drawing a square. Okay, 4 corners. I'm happy. I'm going to hit C for close. And there is my square. Hard to see, but it is living in the YZ plane with an X coordinate value of 0. And in order to make you appreciate this a little bit more, why don't we hide those background planes that I imported with help of a DXF? Let's go to viewport number 1 and start panning by pressing Shift, orbiting by pressing Command. And let's see that this is completely three-dimensional. So we have our diamond living in the XY plane, flat. We have our triangle living in the XZ plane, upright. And we have our square living in the YZ plane. And that is what happens depending on which viewport you introduce any geometry. And let's start with a different shape besides the free draw. I'm going to zoom to extend. Let's do multiple viewports, which is really convenient. And let's look at the other two-dimensional shapes that we have. So in addition to the free draw, there is the ellipse and there is the rectangle, and it speaks for itself. I can click somewhere within my model view, insert a rectangle, and notice that the rectangle will have a certain depth and it will have certain width. It will have X, Y, and Z coordinates, and that is pretty much self-explanatory. The same is true if I were to introduce an ellipse. If I choose the ellipse, then I'm going to introduce a two-dimensional shape. Let's zoom to extend. It again has a depth and a width. Currently the depth, or D1 and D2 if you will, currently is 10 and 5 meters. But if I want it to be a circle, then I need to make both dimensions the same. And notice that it's stuck in the XY plane. So there you have your two-dimensional shapes. And that brings us to the first modifier that we're going to use. And to do so, I'm going to open a different project. I'm going to close this project. And I already have a project ready that has several of these two-dimensional shapes. And for all I know, this could be the floor plan of a church, a typical European Gothic church. We have a ambulatory, we have a transept, and we have a nave. And these are three rudimentary shapes. And now I want to turn them into a single two-dimensional shape using today's first modifier. So why don't we start by choosing the transept and the nave and turn that into a single two-dimensional shape by using the trim modifier. So I have two two-dimensional shapes selected at once. I'm going to hit trim and notice that everything turns white. And what I now can do is I can click on the line segments for which I no longer have any need. And those are the 4 ones that I selected just now. All that I have to do at this point is hit enter. And that leaves me with a new free draw shape that replaces the previous 2. And this is a more complex 2-dimensional shape that I made simply using the trim feature. So now I'm going to select this new free draw and the remaining shape. I'm going to hit trim once more, and I'm going to select a couple of line segments that I no longer need for the outline of my floor plan. I'm going to hit enter once more, and within a matter of seconds, you have a fairly complex 2-dimensional shape, but it's still flat. It doesn't have volume. So let's use a different modifier known as extrude. Let's call this our floor plan for all I know. Okay, this or floor outline. Let's call that floor outline, and let's extrude it linear. Let's give it height. Let's extrude it linear along the z-axis, and let's say 10 meters or so. If I now press apply, then suddenly my 2-dimensional shape becomes a 3-dimensional volume, and all of that was executed within a matter of seconds. And if I now want to do a prediction, as we learned during the previous roundtable, all that I have to do is click predict. And then all the faces that make up for this 3-dimensional volume will now show predicted energy over space for a particular loudspeaker. But you would also illuminate the entire room with sound, and maybe you're only interested in the sound that hits the floor. So we can do better. Instead of making all surfaces predictable, why don't we go to the object settings of this particular 3-dimensional solid, which it's now, and notice that if I move my cursor over any of these faces, that we have a kind of mouse over effect. Whenever I hover over any of these faces, notice that we see a shade of yellow that highlights those faces. And all that I have to do is scroll down in my list of faces and go to the one that is the floor, which is somewhere around face number 60. So let's call this the floor. And maybe this is the only face that I want to make predictable rather than the entire room. And probably you want to give it an offset unless your ears happen to live on the floor. 1.2 meters is typically considered for a seated audience, whereas 1.7 meters is typically considered for a standing audience. And that concludes our first example of using these 2-dimensional shapes with a trim modifier. And before you know it, you have a 3-dimensional volume with multiple faces that you can predict on at your discretion. And let's look at extrusion a little bit more in depth. I'm going to go to my primitives. I'm going to introduce a 2-dimensional shape. Okay, I'm just going to drop it in there. And it's flat. It doesn't have any volume. However, using extrusion, I can turn my 2-dimensional shape into a 3-dimensional solid. Okay, and the instance that we've been using just now is a linear extrusion. So I'm going to do it once more, maybe 5 meters this time around, and that turns my 2-dimensional shape into a cube, or a cuboid, if you will. There's no need to do this because we already have a 3-dimensional solid that fulfills that purpose, but this is how you turn a 2-dimensional shape into a cube. The same is true if I were to start with an ellipse. If I put an ellipse on the floor with a certain width and a certain depth, I can go to my modifier, I can say extrude, I can give it a certain height, if you will, and before you know it, you see a squashed cylinder. But, this one is a little bit tricky to see because we have a face at the top, we have a face at the bottom, but we only have one edge that connects the bottom to the top, and, it doesn't look really like a cylinder. Well, there are several ways to deal with this. One way would be to activate this for prediction, in which case you see that this is very much a cylindrical shape. As you can see, that would be one way of doing it. Another way of doing it would be to go to File, Project Settings, and then go to Appearance. We can say that for our geometry, we would not like to see the wireframe that we currently have over there, but we would like to see a solid shape. If I now hit apply, suddenly my shape has volume, has mass, if you will, and then I can very much tell that this is very much a three-dimensional volume, a three-dimensional solid. So that is something that you can play with to meet your needs. You can make more complex geometry by doing angular extrusion. And an angular extrusion is a little bit less intuitive, but rest assured, by the end of today's roundtable, you will get the hang of it. So here's what I'm proposing. We're going to draw a circle. Okay, let's draw a circle, put a circle in there. Okay, let's give it some even dimensions or similar dimensions. There's our circular shape. We're going to center it nicely in the middle of our drawing space, our model view, by turning the x, y, and z coordinates into 0. And I want to rotate it. I'm going to rotate it along the x-axis. So I'm going to change my x value into 90 degrees so that the circle stands upright. What we're now going to do is we're going to use extrusion, but this time, rather than doing a linear extrusion, giving it height in a certain direction, we're going to do the angular extrusion. And here's what's going to happen. And in order to make you appreciate that, I need to do a little bit of annotation on top of the screen, because whenever you do an angular extrusion, you need to define a pivot axis. And in this case, the pivot axis is going to be the z-axis. And if we are going to do an angular extrusion, then we're going to do a pivot in this direction, clockwise or counterclockwise. I keep forgetting, but we're going to pivot our shape, our circle around this pivot axis with coordinates x, y, 0, 0. And that's where the pivot axis lives. Let me clear this up and show you what happens if we now do a 180-degree angular extrusion around the pivot axis living at x, y, 0, 0. It will turn my flat circle, if I hit apply, it will turn my flat circle into a sphere. And that is already a more complex shape as we had before using angular extrusion. And we can take it even up one step further. I can select this. Okay, let's start from scratch, or let's do undo. Let's offset our circle, okay, and put it out of the center by, let's say, 10 meters or so. Or let's make that even 50 meters. Now the interesting question becomes, if we go to that first viewport with the isometric view, now the question becomes, if I were to do the same angular extrusion, what happens to my circle? So I'm going to keep the same pivot axis. This time around, we're going to do an angular extrusion, and that will turn our circle, if you're, let's wait for it, that will turn our circle into a donut. So depending on where I choose my pivot axis, I can make some very interesting shapes. So let's choose our ellipse. Let's go to extrude. Let's keep the same pivot axis at x, y is 0, but now do a 360-degree extrusion and hit apply. There is your donut shape, using the same circle but offset out of the center. And let's see that in 4 viewports at once. So there you see that same donut shape in all 4 viewports. So there you have your angular extrusion, which brings us to the 3D solids. So I've got a cube, I've got a cylinder, I've got a trapezoid, and I got a half octagon. All of this is covered extensively in the Mapp 3D, but basically these shapes speak for themselves. They have depth, width, and height, and the same is of course true for the cylinder, which has a width and a depth and a height, or in this case it has a radius, as you can see, a radius and a height, but these shapes are all pretty much self-explanatory. There is your half trapezoid, or your trapezoid, I should say, and even the half octagon. These volumes pretty much speak for themselves. Basically, your extrude and trim are primarily intended for two-dimensional shapes, whereas the union, intersect, and subtract modifiers are intended for three-dimensional solids. Let's have a look at that. So here we see 2 shapes. In the middle, we have a cylinder. Here we see our cylinder living in a cube. We're going to look at our modifiers. Now, our modifiers, like trim, always operate on 2 objects at most. So let's select the cube. Let's select the cylinder, both at the same time. Okay. And let's look at union first. So union is going to combine both volumes into a single volume. So if I now hit union, we're going to get a new shape, and that new shape is now the combined volume of the cylinder and the cube. And in order to make you appreciate that more, let's make them predictable, in which case you see that this is now a single volume made out of a cylinder and a cube. So there you see your first Boolean operation. So let's undo this. Let's start with our cylinder and our cube once more, and let's look at one of those other operations. I'm going to select both at once. I can do a drag and select. And the next one we're going to do is subtract. And subtract is pretty much doing what you think it does, which is subtracting one volume from the other. So if I now click subtract, I can choose to subtract my cylinder from the cube or subtract the cube from the cylinder. Well, let's do the former first. Let's select the cylinder, and what is left over is a gap in my cube, which is where the cylinder used to live. So now we have a new three-dimensional solid with a hole in it. The cylinder punched a hole into my cube like a die. So let's undo this, and let's do it the other way around. Let's make these guys predictable. Okay, select both shapes at once, do subtract, but this time around, subtract the cube from the cylinder, which cuts my cylinder in half. There's a gap where the cube used to live, and now we have two cylinders that are separated by the cube that is no longer there. So there's your other Boolean operation that allows us to modify three-dimensional solids. And the final instance is the intersect. And when you use the intersect, here's what's going to happen. Let's select both shapes at once. And now we're going to do intersect. And what intersects does is it's going to preserve the volume that is mutual to both shapes. So the cubic meters and the cubic feet that they have in common are going to be preserved when we hit intersect. So if I hit intersect, I'm going to be left over with a smaller cylinder, which is basically the cylindrical volume that was living within my cube. And that concludes your intersect Boolean operation. So union, intersect, and subtract are all intended for three-dimensional solids. And finally, something that we would like to bring to your attention is, how do I change the centroid? Let's introduce a two-dimensional shape, as we see over here, okay? And that gizmo, that gimbal, okay, let's put that nicely at 0, 0, 0. That is the pivot point. If I were to rotate this two-dimensional shape along the x-axis using my up and down keys, okay, then it becomes a seesaw. I'm using my up and down keys, and I'm turning this into a seesaw around the x-axis. The same is true for the y-axis. If I do the y-axis, okay, then we get a seesaw along the y-axis, but always pivoting around that centroid. And the same is true along the z-axis, which allows me to rotate the object again around that blue z-axis. But there might be a reason why you don't want to pivot or rotate around the centroid or gizmo where it lives by default. So how do I change that? How do I relocate that centroid to a different point or a different position within my shape? Well, the process goes as followed. We're going to do a right click, and rather than using select object, we're going to do select vertex. So now I can choose the individual vertices that make up for my two-dimensional shape, including the midpoints of the line segments. And if I want to relocate that pivot point or gizmo or centroid to one of these vertices, then all that I have to do is select one of them and hit enter. Okay? And now I need to go back to the select object mode. If I were now to select my rectangle again, you notice that my gizmo is no longer living in the middle of the two-dimensional shape, but is now relocated to the corner that I designated. It also means that if I now were to rotate my shape, that I'm no longer rotating around the X, Y, and Z axes that you see in the middle of the model view, but I'm now rotating around that new position. Okay, now it's no longer a seesaw. Now it's more like a whatever you want to call it. I'm lost for words. I can do this for a two-dimensional shape, but I can also do this for a three-dimensional solid. So let's drop a three-dimensional solid next to it. Notice that the centroid lives at the center of mass of my three-dimensional solid. But if I want to relocate it for whatever reason, I'm going to repeat the same process. I'm going to select my cuboid. I'm going to go right-click. Rather than select object, I'm going to do select vertex. And now I can choose any of the corners that make up for my three-dimensional solid, including the midpoints in the line segments that connect my vertices. Okay? And if I'm happy, I'm going to hit Enter, right-click, select Object. And if I were to select that cuboid again, you now see that my gizmo, my gimbal, my pivot point is now living at that chosen position. And that is where I can now do manipulations such as rotation and whatnot. However, if for whatever reason I want to return that centroid to its default position, all that I have to do is click in the model space, model view on that particular shape and press Shift-C. And with Shift-C, that centroid goes back to the default position. Same is true for my two-dimensional shape. Currently, it's still living in the corner. If I were to select it within my model view, hit Shift-C, then it goes back to its default position. We're going to go at SPL versus attenuation in model view. So if you go to your project settings and you go to the tab called SPL, you will notice that there's two ways that we can show the distribution of energy over space. There's attenuation, which has always been there since the very beginning, and there is SPL, which is an absolute scale, whereas attenuation is a relative scale. When you look at our meters, then we have a white color that basically constitutes the top of the scale, which I like to think of as clipping. It's the maximum attainable level that we can show. And at the bottom of the scale, we have our minimum, or the floor of the scale, which will always be shown with a black color. The difference between maximum and minimum is what we call range. And range is something that the user can set themselves. By default, it goes to 42, the difference between maximum and minimum. But we can also change this to a different value, which is very expedient. That being said, there's also an absolute scale, which is SPL, where the ceiling in this example is 110 dB SPL, as in sound pressure level, and the floor is living 42 dB below it. And that comes with certain things that we need to take into consideration. In attenuation, what we're dealing with is that our range basically determines how much peripheral view I have, or how much I see of my environment. So over here we see a circle that has a radius of 32 meters, and that gives it a diameter of 64 meters. And at the center, I have an omnidirectional source. And as you know, an omnidirectional source radiates equally in all directions. Let's go to 125 hertz. And let's bring up a piece of geometry that covers my circle. And let's do our prediction, and then we can all be mesmerized by the omnidirectional source. So I'm going to hit predict, and then we're going to expect to see the propagation of SPL over our circle. Okay, so there we go. So there you see your omnidirectional behavior. Let's go to viewport number 2. Notice that currently we are in SPL. I'm going to get to that later. First, I want to tweak some settings to make more sense out of this. So I go to my project settings, I go to appearance, and I'm going to play with the opacity setting, which determines me how much I will see of my DXF underneath. Because now we can see the underlying shape that we have in there. And what you can see is these concentric circles. And for those that are familiar with the inverse square law, which dictates that the sound loses 6 dB of pressure when you double your distance, we have a circle. So our outer circle is at a radius of 32. Then we have 16. Then we have 8, 4, 2, and so on and so forth. And I can make you appreciate this by going to attenuation first. So let's go to right-click, set max SPL. And we're going to look at attenuation first. I'm going to start with manual. I'm going to set it to 12 decibels. That's going to be the range. 6 dB per color divisions. I'm going to hit apply. This doesn't require recalculation. This only requires remapping. So this is not going to do a full recalculation. So let's wait for it to update. So now we only see up to 4 meters, because from 1 to 2 meters is a 6 dB loss, and from 2 to 4 meters is another 6 dB loss, and then we go to black because we're off the scale. So we see very little of our surroundings. And the maximum, the peak level in attenuation is always determined by the loudest level on an activated prediction plane, which in this case is, of course, any of the positions closest to my omnidirectional source. But watch what happens if I make my 12 18 decibels. Then I'm going to get another ring. Now I get to see up to 8 meters. And I'm doing it in high resolution to really make you appreciate the accuracy. So now we have another ring, another 6 dB increment. We go from 1 to 2, from 2 to 4, from 4 to 8, and every time we do so, we lose 6 decibels. Let's add other 6 decibels of range, and that is going to get us another ring. So there you see attenuation right in front of you. Now we're going to get another ring, which is the ring from 8 up to 16 meters in 6 dB increments per color. And finally, let's go to another 6, which is going to be 30. And now we're going to see another 6 dB increment all the way to the edge of our circle at a radius of 32. And every time we go from 1 to 2, from 2 to 4, from 4 to 8, from 8 to 16, we're going to lose another 6 decibels of propagation loss. So there you have attenuation right in front of you. Okay? Beautiful concentric circles. And attenuation has always been there. But what is new is SPL. So let's go to full resolution and let's go to SPL. Now what changes is that suddenly my scale is no longer relative, where the loudest value is determined, where the top of the scale is determined by the loudest position on the listening plane, which is typically very close to the loudest loudspeaker. Now the scale becomes absolute. If I now hit apply, suddenly my scale is going to change from attenuation. It's going to show SPL. And what we're going to see is 42 decibels of range, but the ceiling, the top of the scale, is now determined by whatever value is living in that cell, which says max value. And that means that you might see shades of white. Currently, we don't see shades of white because the scale completely captures the energy that is being produced by our omnidirectional source. But if I were to turn the ceiling down to 80, we're going to see part of our prediction plane will now be white because those values now exceed 80 decibels, and they will be shown in a white color rather than in a black color. Yeah. This entire portion is now off the scale. This entire region is now showing you values that exceed 80 decibels SPL on an absolute scale. Go for Josh.
Hey, Merlin. So one thing that's really awesome and really cool with this new methodology is you can now set attenuation to, say, 12 dB SPL and 3 dB or 6 dB per color. And that gives you sort of a great, quick way to pass-fail your placement of loudspeakers to line up the negative 6 dB down points for unity gain and equal placement.
So I want to go to the first viewport. If we look at my SPL settings, I'm using a range of 12 decibels. I'm going to use 6 dB per color division. I'm going to choose my main left speaker, and I'm going to do a prediction. And what we now will see is we will only see two colors. Two colors, where red is the area that is covered within 6 dB or less, and blue is the area where you see 6 to 12 decibels, okay? And we always like to make -6 meet -6. So I can instantaneously see in this example that this loudspeaker is essentially sole custodian over one half of the room. And then, of course, the other guy is going to be sole custodian over the other half of the room. And together, in this particular example, they will cover the entire room. So if I now select main left and main right at the same time and do another prediction, then you see that the macro shape is covered by our main PA pretty well, okay? But only the people that are living in the red area with 6 dB per color divisions using a range of 12 decibels are within 6 dB of variance or less. So that is a very easy pass-fill system. I can also use the same approach for my front fills. I've got front fills living over here, and if I do a prediction of that front fill, okay, and we go to the top view, if we go to the top view, then we see that only the people living in the red region are within 6 dB of variance or less. And that means that between these adjacent front fills, my contour that separates red from blue should meet the level of the other guy. So if we were now to select both at the same time, I can really discover what the spacing is that I need between adjacent front fills to make them cover that first row together. So that is super convenient. And if you're familiar with lateral aspect ratio and whatnot, then this becomes really a very nice tool to confirm, is everybody within 6 dB of variance or less. So now we see the entire front fill system at once, and you see that the first 2 to 4 meters are beautifully covered. Now we can go to the entire system and give it a pass fill by selecting everything at once and have a look at that. So now you see that everything is, the vast majority of our venue is within 6 dB of variance or less, and you might need an outfill to cover those corners. We need to be mindful that at all times that the SPL that we see is proportional to the bandwidth that we're predicting. And remember that in Mapp 3D, okay, this is where we set our bandwidth, okay? 1/3 octave, 1/6 octave, 1/12 octave, 1/24, or a whole octave. That's where we set it. And that means that within 1 octave, there's more power contained than within 1/3 octave. So when you're working in SPL mode, the values that you see are now proportional to the bandwidth that you're predicting. And that means that all things being equal, if I go from 1 octave to 1/3 octave, that there is 3 times less power within that interval, which constitutes a 5 dB drop in level. If I now were to go from 1/3 to 1/6 octave, then there's again 2 times less power within that sixth of an octave. I'm going to lose another 3 decibels. And that means that by the time I'm looking very narrow banded, that my SPL appears to drop. But that's only because you're looking through a telescope. You're looking at a narrower frequency range. And as a result, there's less power contained within that narrow frequency range. And it looks as if your SPL is diminishing. The only way to see broadband metrics is to drop in a microphone and go to the headroom top. When you're working in model view, even if you're working in SPL, then you're always looking at a level which is a function of the bandwidth that you are predicting. If you want to see broadband values, dBA weighted, dBC weighted, dBZ weighted, as in zero weighting, okay, for the entire audible band, you need to drop in a microphone and you need to go to your measurement view, more specifically to the headroom top. Tweaking SPL settings for quick design is essentially the pass fill method, which we already saw. Set your range to 12 decibels with 6 dB increments gives you a pass fill approach. There's one more topic that I would like to discuss with you, which is how can I increase the prediction speed? In Mapp 3D, prediction speed is proportional to 4 things. Of course, there's the mesh density. The mesh density is the very thing, if we go to our appearance, the mesh density ultimately determines the resolution or the number of prediction points, if you will. And of course, if we have very high resolution, we need to do more number crunching, whereas if we have very low resolution, then we have to do less number crunching. So it's readily apparent that calculation time is proportional to mesh density, but it is also determined by the number of visible and activated, as in activated for prediction, the number of visible and activated faces. The more faces that are visible and both activated, the more number crunching you need to do. And of course, if I have a larger area with the same density, then I have more points to predict, whereas if I have a smaller area with the same density, then I have fewer points that I need to predict. So also the area of those visible and activated faces will affect the calculation time. So as your models get larger, like physically larger, things are expected to take longer. And finally, it is proportional to the number of, again, visible and unmuted loudspeakers. You can have 100 loudspeakers in your model view, but if 99 are muted, then it's still going to go rather quickly. Whereas if all are unmuted, it's going to take longer. So only things that are visible, only objects and layers that are visible are taken into account. And faces need to be activated and loudspeakers need to be unmuted. However, changing SPL settings Post-prediction does not require a full recalc because it's only a rendering challenge. It's only remapping. So if you're talking about how do I expedite the predictions, well, lower the resolution, reduce the number of visible and activated faces by maybe designing only half a venue. And then once you're happy, if symmetry allows for it, once you're happy, then mirror everything and turn it into a whole venue. And of course, reduce the number of visible or unmuted loudspeakers or the loudspeakers that you're selected rather than doing all of them once, only do a few. And this is pretty much self-explanatory. We're going to go to Alex, and Alex is going to conduct a short demonstration of all those techniques at once.
All right, so we are going to combine a few of the techniques that Merlijn talked about, specifically extrusion and intersect, and we're going to do it in a real venue. I'm not going to tell you what venue this is, but it's a generic theater. You can see from this isometric view, it's a one balcony theater, some rakes, and we were provided plan and section drawings. But I want to make a 3D model out of this. And the first thing to note that I noticed when I was looking at this drawing was that the seating in this venue is curved. So if I were to use linear extrusion, it would not be accurate to the geometry of the seating in this venue. So we're going to use angular extrusion. And that's a little more difficult, but it just takes a few values that we need to find out to do that extrusion accurately. So when I was preparing this model in CAD, there is something I like to do before hitting Mapp 3D, which is creating a layer of reference circles. And I did this in AutoCAD, which is really easy with the 3-point circle tool. And I needed to find the center of rotation that they made the curves of the seating with. So all I did was pick 3 points on the front of the stage right here for the main level in the front seating section. And I found the circle that completes that arc. And I marked off, it's kind of hard to see here, I marked off the center of that circle kind of roughly. So what I like to do is use the snapping tool and the free draw to find the coordinate of that point of the center of the circle. I also did that for the balcony face with the second circle. So just using the snapping tool, I can check those coordinates of those two. I drew a line between the centers of each of those circles so I can get the 2 points. But either way, the point I care about for the front of the stage is negative, let's call it negative 13.7 in the X dimension. So I'm going to keep that in my brain, 13.7. And now we're going to define the areas we want to predict on, right? So specifically, that's where people are sitting and where listeners are. First, I'm going to draw an audience profile, we call it, which is basically tracing in the section view where all the seats are. And I'm going to do that per level. And for this example, I'm just going to use the orchestra level, the main floor. So let's just draw where people are. Let's not draw empty floor. Let's not draw the stage and steps. Let's just start at the first row. And just for simplicity, I'm going to start where this step starts. And we're just going to kind of trace the rake of that. Let's say right here-ish. And that rake gets a little more steep. And just for simplicity, I'm going to call this a 2-angle rake, right? So I've defined on the main level where my seating is, and I'm pretty much done. So I can just hit enter in the free draw tool to make that a 2-segment line. And I can see here, it's aligned to the center line of the drawing. As Josh mentioned, this is part of that snapping in the 4-panel views. I drew this in the section view and snapped it to wall 0, which is pretty handy. This is the first part of the cookie cutter method. We are going to roll out our dough first, and we're going to roll it out with accurate angles to the curvature of the seating. So I remembered that 13.7 value, and I am going to have this audience profile selected, and I'm going to extrude, and I'm going to do angular extrusion. You can see I practiced this before this, so I already have that 13.7 entered. And the angle that we roll out our dough and how far we go out with the audience area is arbitrary here. The main point that we want to do in this extrusion is make it past the sidewall, because in our cookie cutter, we're going to make a cookie cutter that is the shape of the venue and stamp out what we want to keep. That's the cookie cutter method. So I'm just going to pick an arbitrary 60-degree angle here, and we extrude it out. I picked where the first row starts, and so I'm excluding a bunch of empty space in front of that first row. This is one thing to note on what Merlijn was talking about with front fills and the kind of pass-fail method. Is one caveat to that is when you're using attenuation, the loudest point on the audience plane, you want that to be where a listener is and not 6 feet in front of a listener, because then you're judging places where people are not listening, and you might be putting your speakers tighter or wider than they need to be. So that's just one thing to note. I would say when drawing audience areas with listeners in mind particularly, is not to make it extend way past where the listeners are in determining spacing of loudspeakers. It's certainly useful to predict on places where people are sometimes. So we have rolled out our dough, and we can see it fits the curvature of the front of the venue pretty well. We don't have much reference to know what the back of the venue is here, so we're just going to go with this for this example. Sometimes seating is shown back here, and we might have to do 2 different curvatures, which gets a little more complicated, but we can talk about that in a future session potentially. This is a good chance to show that angular rotation that we mentioned. So I could do half a venue and just cut this off right here, like I usually do, and then mirror it. But just to show it, let's say I wanted to center this back to the center line. So I extruded it from the center, and now I want to bring it back. And that's really easy to do if I want to do a polar array. And I'm just going to pick that negative 13.7 value again. I'm going to make 2 items. I'm basically going to teleport copy, this object back to where it was. So I remembered I did 60 degrees, but I want to go backwards half of that. So I'm going to go backwards 30 degrees here. This is just a simple example of that. And I'm using the same rotation reference point, and I'm rotating the objects around that reference point. It would just shove that without rotating it otherwise. So if I do this, now I've rotated that back to center. And to spoil the movie Prestige, if you teleport something, you have to destroy the original copy, right? Or the original. So we have extruded that back to the center, and now we can make the cookie cutter of this. So I'm going to go to the plan view, and all I'm going to do now is I'm going to trace the walls, essentially where the seating would stop. So one thing to note is in this cookie cutter, where the curvature is already accurate, like this front seating section, we don't need to cut out that area. We really only need to clip off this little triangle pizza slice that comes outside of the actual model. So what I'm going to do is make a cookie cutter that's larger than the areas that I want to keep. So I'm just going to pick arbitrary points and make lines that cut along this sidewall. And now I'm outside. So when I'm drawing this shape, it doesn't really matter where I pick, but I just need to be able to draw that angle again on the opposite side and go back out. And so all this stuff I want to keep, I'm pretty good with that. And I have my cookie cutter. I can just hit the key C for close, and I've made a closed free draw shape. So I'm going to linear extrude that vertically, and that makes a cookie cutter. But the first thing to note is when I traced that audience section, it went below Z equals 0, which is what this cookie cutter trace is at right now. So what I need to do is make sure that that cookie cutter contains all of the vertical sections of my rolled out dough, so I don't lose that front section. So what I'm going to do is select, just that free draw. And I'm going to bump it down a few meters.
Using your up and down keys, right?
That's correct. Yep, I just used the down key to just bump that down a few meters. And you can see the selected object is now below the rolled out dough, right? So I can easily just extrude this in the Z axis. Let's do another arbitrary value of 15 meters. Let's just make sure it includes all of the vertical information of that section plane that we've made.
Yeah, your 3D solid should completely contain your 2D surface.
Yep. So I'm going to go to full view mode now. Oops, this one is what I'm going to do. And using the S tool, the S key, I can flip between solid and wireframe view. It's a little easier to see what's going to happen now is I'm going to keep everything that's inside of that cookie cutter that I've made, and everything else outside of it is going to get clipped off. And the magic of this is the intersect command. So if I select both of those objects and I intersect the thing, I'm going to keep what's common between both of those and throw out everything else. I'm going to throw out all of the gunk of the rest of the cookie cutter and the edges that it's clipping off. Just hit intersect, and that's the magic. I'm left with a accurately curved audience area that ends at the sidewalls and accurately represents the curvature of seating versus a linear extrusion, which if I tracked the first row and just went straight out, the same elevation would be right here when I know that same elevation is curved with the stage and right here. So you could be potentially doing some inaccurate decisions with your model if that geometry isn't accurately represented with curvature and more complex things than just linear right angles and stuff. Like that's the quick cookie cutter method, and there's lots more ways to do more complicated compound curves with like stitching together two parts that I've done that is actually just a simple duplication of this technique and making the meeting point of the two curves align well. But as you can see, this is, I took some time explaining steps, but you can do accurate listening planes very quickly with these steps of defining where the listeners are in the vertical plane, extruding that accurately along the curvature, if there is curvature, and then clipping off where that audience plane exceeds the room or where your listening plane is by cookie cutter stamping out the excess that you don't need.
And Alex, one thing that we've talked about before is if you don't have CAD and you're just getting the drawings and you can't input these circles that you've had, one way you can do this is inserting a 2D primitive circle from Mapp 3D to find where these curvatures would go. So that's a simple, easy way to also find where this pivot point is for these angular extrusions.
Right, especially if you use the right-click menu and insert geometry, then depending on your viewing axis or your camera angle, then the geometry will automatically end up where you right-click within your model view.
How did you choose your pivot axis for angular extrusion? I mean, what if I want to extrude along x-axis instead of z-axis as you did? Does it only depend on my viewport?
Angular extrusion is locked to XY plane. It makes it simple that way to do what I showed in my example. But if you did need to have a rotated surface outside of the XY plane, you could certainly just do the XY rotation and then rotate that object once it's created.
Is there currently a way to choose solid versus wireframe per object, or is it global only?
As far as I know, it's global.
It's global for geometry, or I should say there are separate settings for geometry and loudspeakers, not per object.
This is true. So if we were to go to our settings, if I were to go right click and we go to appearance, then we have wireframe or solid for geometry, and we have wireframe or solid for objects such as loudspeakers and microphones. For Alex's examples, did he add two DXFs? Or did he take a section and a plan view and put them together in AutoCAD?
I created that in AutoCAD, yeah. I took the plan and section drawings and I used the Rotate 3D tool in AutoCAD to stand up that section as kind of a faux 3D model, giving me those reference things. And most importantly, I aligned them so that they would be, the stage would be accurate in section and plan view. So that allowed me to be accurate with those extrusions and things between plan and section.
Right.
What would be the difference in terms of the behavior of prediction between the 3D objects made from primitive and from 2D extrude function? I think, Alex, we could talk about the triangles and the way meshing happens. And sometimes you can get those mesh flares. You could probably predict that a little bit better.
So when I had prepared that example, I had made a few examples of inaccurate ways I could have modeled this venue. And this is kind of a good example of some kind of aberrations that can happen through the meshing in the triangles that Josh mentioned. So the way I did this inaccurately was I first just traced the plan very roughly in the plan view, and then I went and modified the Z values of where I knew the beginning and end of that plane were. So I basically just tilted a flat plane. And since I did free draw and just forced that into an angle, I didn't really make a totally flat surface. I just sort of bumped different parts up and down, and it might look flat, but Mapp is telling me that it's not really flat through these little clips and gaps that you see in the prediction. What you do when you predict into Mapp is it has to take the audience areas and it has to mesh those into triangles to accurately determine the SPL that's going to end up on those triangles. So if we just do a free draw and force it into a 3D-ish shape, Mapp has to do that meshing and cut that into 1,000 little triangles every time you hit predict. So this prediction both took longer and isn't accurate and gives me weird things like these little gaps in the prediction area, as well as things that just shoot out weirdly. So in addition to being accurate to geometry, that angular extrusion and then the cookie cutter method does that meshing when you create the object instead of every time you hit predict.
Since we were talking about predictions, I recall in Mapp XT there was a quick screenshot tool for taking pictures of the prediction plane. I found that useful. Does that functionality in Mapp 3D exist?
So it would be your export model view screenshot, which would be Mapp 3D's equivalent function. If I click on that, a dialog opens, and that only exports the SPL in the model view, including the scale or not. That is something that you can change. And then there's different formats and different resolutions, which will determine ultimately the file size.
And you can do the same thing for your measurement prediction. So where you place your microphone, if you want to show headroom, say at my microphone right here, this is what I would expect when I get on site. And we challenge you to put it there and hang the speaker in the right place and match your settings in the real world versus Mapp 3D.
We have 2 more roundtables scheduled, which is Thursday, September 17th and Thursday, September 24th. Same time, same day. And for all we know, depending on your feedback and your user experience, we might actually schedule additional roundtables. That means that next week, we're going to talk about how to interpret Delta DB, which is also a new feature in Mapp XT, not present in, in Mapp 3D. Did not exist in Mapp XT, apologies. And as Josh already hinted, we're going to look at the connection to Galileo Galaxy devices, Compass control software, and Compass Go all at the same time and see how they speak to each other in near real time. And that means that I'm going to suggest that we call it a day. We're very much looking forward to seeing you 1 week from now. On behalf of Meyer Sound and my fellow panelists, thank you for watching. Please stay safe and healthy, and best to you and your loved ones. Bye-bye.